Hi everyone, welcome to the second part of our Unit 9 Remediation series. Here we're going to be looking at physical change math related to heat and energy, specifically using those heat equations on table T to help quantify how much energy is required to change particle spacing, or maybe even the speed of particles. So in order to do this, the first thing we really need to understand is the idea of these phase change diagrams, and to really intensely analyze what's going on and what's represented by all of these lines. Everyone knows what solids, liquids, and gases look like at a particulate level. Solids, we have very tightly packed, organized particles. Liquids get a little bit more wiggle room, and gases are very far apart, and they are bouncing around doing their own thing. The lines in between are representing the changes between those three states of matter. We know if we melt something, we're going to weaken the attraction of these particles so that they have more space to move about freely, so that liquids can be poured, whereas solids can't. If we go in the opposite direction, we're going to take out some of that energy so that the particles are going back to a more organized state. Likewise, if we boil something by adding energy to it, it's going to turn into its gaseous form. Here we can tell it's going to take a lot of energy to try and pull those particles so that they're so far apart they'll behave like a gas instead of a liquid. Likewise, we have to remove a whole bunch of energy in order to get them back into a liquid state, because there's a whole lot of energy keeping these particles from interacting. So along this heating and cooling curve, what I see is three things. Areas where temperature changes, but our potential energy or particle spacing remains relatively constant, and areas where kinetic energy remains constant, or our temperature remains the same, but potential energy is changing, where particle spacing is either getting slightly far apart or closer together, or way farther apart or way closer together. That's where the three heat equations come from. Our first heat equation, Q equals mc delta T, or the MCAT equation, has to do with those areas in which kinetic energy is changing. It allows us to see how much energy has to be added to a system in order to get a particular change in temperature. So in all three slanted parts of this heating curve, you would have to use Q equals mc delta T if you were interested in finding out how much energy had to be added to create a change in temperature. For the points along the graph where potential energy is changing and temperature is remaining the same, we have to look at how difficult it is to either weaken attraction between particles or completely break apart the intermolecular forces holding particles together. If we're looking at going from solid to liquid or from liquid to solid, the heat of fusion of our substance is going to give us information about how hard that transformation is. Since heat of fusion is only related to 1 gram of a substance, we need to multiply that times the mass of the substance we're interested in order to figure out exactly how much heat we need to add to bring about the change. Over here on the boiling and condensing side of things, we're interested in the heat of vaporization, or how hard it is to get particles to make this drastic change from liquid to solid. Again, heat of vaporization has to do with 1 gram of a substance, so we multiply it by the mass to come up with the third equation on table T, Q equals mHV. We're going to be using these three equations to help solve problems. So make sure you're comfortable figuring out which equation is appropriate for which phase change or change in temperature. Let's look at a couple sample problems to try and figure out how to make use of these three equations. So the problem on your screen now asks you how much heat is released when 200 grams of water condenses. There are three giveaways that you need to be using a heat equation here. First and foremost, the word heat shows up in the problem. We want to know how much heat is released when a particular mass of water condenses. Looking at this diagram we just filled in, what I see is that we're moving from an area where particles are very far apart. We're trying to push those particles closer together to sort of put into play the intermolecular forces in action. So here, what I would use is the equation Q equals mHV. How much energy does it take to get out of the system to make it look more like this? So let's write down the Q equals mHV equation. Now it's just a matter of looking up what those values are. We don't know what heat is, so I'll leave that as my unknown. Our mass is given to us in the problem as 200 grams. And HV is something that normally we wouldn't know, but we can look it up on table B. As you see here, for water and for water only, HV, the heat of vaporization, is 2,260 joules per gram. That tells us for every gram of water, if we want to either turn it into a gas or get it out of its gas phase, we have to put in or take out this much energy. So let's plug in that value 2260 into our equation. 2260 joules per gram. From here, it's just a matter of plugging it into the calculator. 200 times 2260 gives you 452,000 joules. If you wanted to write that in scientific notation, I would put a decimal in between the 4 and the 5 and multiply that by however many times the decimal needs to move. So 1, 2, 3, 4, 5 spaces over joules. Let's use that same thought process to solve a similar but slightly different problem. How much heat is required to melt 200 grams of water? In this case, we'll be putting heat in order to weaken the intermolecular forces holding solid particles together to turn them into a slightly more fluid liquid. So again, I see the giveaway that the word heat is right in our problem. We're melting 200 grams of water. Looking at the graph, what I see is that melting process involves the heat of fusion, how much energy is required to weaken intermolecular forces or to re-strengthen them, going back and forth between melting and freezing. So that equation, I'll copy down right into the front of my problem, Q equals mHF. And again, pull information from my problem and from my reference table in order to solve it. I don't know Q, but I do know M is 200 grams, and all I need to do is look up HF. Looking at table B, what I see is that the heat of fusion is reported as 334 joules per gram, significantly less than the heat of vaporization. And that's because it takes much less energy to just weaken those particle attractions than it does to completely break apart the intermolecular forces, converting water into a gas. So we'll use that smaller value of HF in this particular problem, 334 joules per gram. When I plug that into my calculator, 200 times 334, I get 66800 joules. Or if I wanted to write it in scientific notation, put that decimal between the 6 and the 6 and multiply by the number of times I need to move my decimal place to the right. Put a joules on as units. As you can see, that value is smaller than the amount of heat released when we turned a gas into a liquid, and that has everything to do with intermolecular forces and the spacing between particles. We really had to push particles close together to condense the water. Here, we just needed to weaken the intermolecular forces. So it did take some energy, but not quite as much as it did to make such a drastic change between liquid and gas. For this third problem, the only thing that I'm changing is kinetic energy, how quickly the particles are moving. And I want you to pause this video for a moment, choose which equation you think is most appropriate, look up the values you need from table B and pick out the information that's given from the problem, and try and solve this one for yourself. How much heat is required to raise the temperature of 200 grams of water from 25 to 48 degrees Celsius? So pause the video now so that in 5 seconds or so, I can show you the solution that I arrived at. Hopefully you had a chance to solve, because I'm about to reveal the solution that I got. I chose the MCAT equation, and plugging in values got me to the answer that you see in the bottom right.